And am I audible?
Yes,
Okay. So should we wait for a few minutes or we can start? What? Because no one has joined, I don't think anyone joined. So let us start.
okay.
Okay. Okay. 2 minutes. 1 minute we can wait more. Okay, let's start. So let me first connect this. Okay, I think. Okay, I'm sharing my screen. This part of it is- So is this visible?
Yes,
Okay. So do you have any doubt? Because this is going to happen, this will be our last class, probably, yes. So if you have any doubt, you can ask me. Whatever you doubt you have, you can ask me. Okay.
in the last,
Huh? Yes.
can we ask in the last after discussion of the things that
Yes,
were
yes, that
remaining?
also. Yes, yes, yes. Yes. Because two, three things I have to discuss today, not so much. Because I promised to discuss about that thing. So after that, you can ask me. Okay.
Okay.
Okay. So let me start. Okay. So proof that the number of quantum states available to a system is way more greater than the number of particle present in the system. So in last class, I said that there is a classical limit, right? Under classical limit, what happens? That under classical limit, our FD statistics or both Einstein statistics, statistics, which are basically quantum valid for quantum mechanical particles, these statistics essentially reduced to our Maxwell-Boltzmann stat, right? This is our this is called classical limit. So how the classical limit is defined? Classical limit was defined like high temperature, low density, and large mass. These three are the main condition to defining the classical limit. So if these three conditions are valid, if the temperature of the system is very much higher and the density is low enough and the mass of the particles are large, this is also not very strict condition, but still. So then you can say that FD or both Einstein statistics will be reduced to our Maxwell-Boltzmann statistics. Maxwell-Boltzmann statistics is essentially uh, classical statistics, valid for classical particle, not that means the particles which don't have any spin or any quantum analog, distinguishable particles. These things we have discussed in the last class. Okay, so and this class under this classical limit, how we define that? If you consider the classical limit, what happens? GI was very greater than NI. These things we have discussed, right? That means GI means the number of degenerate state present under a particular energy level epsilon I. Let's say there is a energy level epsilon I, and under this energy level there are so many number of degenerate state present. Why we are considering the degeneracy here? Because we know that if there is no degeneracy present in a system, then for quantum mechanical particle, obviously the omega, the probability micro number of microstate will be 1. That totally depends on the degeneracy. So this is the number of degenerate state, that is GI. This energy level is epsilon I, and the number of particle you have to put in this energy level, that is Ni. So eventually when GI is very greater than Ni, that essentially signifies the, and this is valid for each and every I, not only for particular one energy level, that this is valid for any energy level. So this is a generalized statement. Okay, so that so then it will be called a classical limit. Okay, so GI should be very greater than Ni. So what does it mean? Why it is classical? Why it is called classical limit? Because when GI is very greater than Ni, then it means that for a particular particle, or if you consider one particle, there is a huge option for that particle. That particle has a huge option to be sit in the any energy state. There is a way more options. Okay, so this is called the GI. This is justified by this inequality GI very greater than Ni, and that we have to show here. That I have written here. The number of quantum states available to a system is way more greater than the number of particles present in the system. So we will not show directly. We will consider a hypothetical condition, not hypothetical, a different condition which is more easier to understand. That condition we will take and we will study. We will establish that when we consider the classical limit, then obviously we consider this high temperature, low density, and large mass. We can show that GI will be very greater than Ni. That we have to show. Okay. So till now, is this clear? What we
Yes.
what we will show here? Okay. Okay. So so we will consider energy states. of particle in a cubic box. So this system we have choose. Okay, any system we can choose, but for under the for this system we will show it. Okay, so we are considering a cubic box and we are considering the energy levels. You know, for cubic box the energy levels, what are the energy levels, and we will show that under that classical limit what we have discussed, then AGI will be very, very greater than NI, that we will show. Okay, so and the length of the box is A, that you know we are considering cubic box of length A. That means you can consider like this. Okay, so this is a cubic box eventually, and the length of these edges are A. So you know for a cubic box what are the energy level. This is we can obtain from quantum mechanics. What is the energy level? That E will be nx square h square by 8m square plus ny square. In general, it is actually the lx square n square h square by 8m ly square and nz square h square by 8m lz square, right? If you consider unsymmetrical three-dimensional box. But as it is a cubic box, so length will be same and that lengths are given as A. So it will be a square, a square, a square. So you can write E, Nx, Ny, Nz, these three are the quantum numbers, and it will be h square by 8m square. If you take common, it will be nx square plus ny square plus nz square. So you know this will be the energy energy of the quantum states. And you know nx, ny, nz, these are the quantum number which value which can take 1, 2, 3 these values except the 0. Okay, these things you know. Okay, so now among these three quantum numbers, we are choosing only two. First, before that, let me write down the energy states. What will be the ground state? If you consider this is a k, then it will be, let's say, k into nx square plus ny square plus nz square. So then what will be the ground? What will be the energy levels? So what will be the ground state? What? Obviously, 111. That should be our ground state. These things you do have studied in quantum mechanics. Particularly in 1D box you have studied, right?
Yes.
So just similar, in case for 3D box there will be three quantum numbers. So this is actually the nx, ny, nz. What I will write nx, ny, nz. This. So when this is 111, so that then energy will be eventually 3k, right? If you put here, so you will obtain 3k. So this is our ground state because 0 is not allowed. So this must be our ground state and this is non-degenerate. What will be the second state? Second state should be, let me draw in next page. Then we can show other levels as well. Okay. So, so we had started with our ground state, which was A111, and energy should be 3k because energy is k into nx square plus ny square plus nz square, right? What will be the second, first excited state or the second state?
2-1-1. 1-2-1 and 1-2.
Exactly, exactly. So it will be 1-2-1, 1-1-2, or 2-1-1. For each case, the same value, energy value will be the same. So these three state will be degenerate state. Okay, and the energy will be obviously 4 plus 1 plus 1. So it will be 6K if you put it. So this is our second state. Then third state will be 2-1-1. Again, it will be threefold degenerate. 2-2-1, 2-1-2, and 1-2-2. What will be the energy? Total energy will be 4-4-1, so 9K. And it will be also a threefold degenerate state, right? 1, 2, 3. Threefold degeneracy will be there. So in this way, you can calculate the energy states present in the system. Next state we can easily calculate because next state will be 2-2-2. Where 2-2, if it is 2-2-2, you have to calculate. So then energy will be, epsilon will be 4-4-4, so 12K. This should be the correct answer. What will be the next state? This type of question regularly asked in our net and gate, because here many trivially it can seems that next state will be 2-2-2, but it's not.
1-3-1.
Just a 1-3-1, it will be 11. If you add it, then the total energy will be 11K. So next state will also be threefold degenerate. So you have to be very careful to calculate it, because it's very common to make mistake. Okay, so it will be 3-1-1 or 1-1-3 or 1-3-1, and the energy will be 11K. And the next state will be obviously 2-2-2, and this is a non-degenerate state, 12K. And in this way, you can also calculate the upper excited states as well. So you have to obviously be careful. Okay. And one thing I should mention here, this degeneracy, you can see here, this degeneracy, one, let's say these three states are degenerate, right? So these degeneracy are called normal degeneracy, because if you look at the expression of energy, it's evident 2-2-1, 1-2-2, and 2-1-2. These three will have the same energy, obviously, right? From this expression, you can see here, it will evident. It is common, but there is called something called accidental degeneracy. There is something called accidental degeneracy. Can you give an example? Any example of accidental degeneracy? That means that is not very straightforward to have degenerate state under that energy level, but there is a degeneracy. Can you give any example? Let me show you. Just consider the energy state which has the energy 27K. If then, what are the states which have the energy 27K? Do you get it?
3-3-3.
Yes, 3-3-3. So at 27K, so there is an energy state which is 3-3-3. Any other?
1-1-5.
Yes, 1-1-5, 5-1-1, and 1-5-1. So there will be four degenerate states. So you can see here, these three will have the same energy, it's clear. So these three are not the accidental degeneracy, but with these three, these states has the same energy. So this is called the accidental degeneracy. This is not evident. This is just accidentally happened. Okay, so this is called the accidental degeneracy. Sometimes they ask the number of accidental degeneracy present in that energy level. So these questions are asked. So you have to be careful about what is meaning of accidental degeneracy. This is not uh, normal degeneracy. Okay. So this is not
What is
accidental
the number
degeneracy.
of accidental degeneracy?
What is the number of accident? Four, four. Obviously four. So how it is four?
The
So you can
total.
yes. So you can say like this: 333 has accidental degeneracy with 115, with 151, and with 511. So there are four accidental degeneracy. Okay. In this way, you have to, or you can directly understand that under that energy level, if you have the accidental degeneracy, you have to just put the number of degenerate state present under that system. That will be accidental degeneracy. Accidental degenerate states are there. So this type of question has been asked. Already this question was asked when I was appearing in a NET exam and I gave a wrong answer. Okay, I put this three was, but I forget this 333 was also a option that I forgot.
But it has no degeneracy. Only those three has degeneracy.
No, but degeneracy means under that energy level, number of energy states present. So there will be four states which will have the same energy, 27K. If you go with this ladder, one time you will find there will be energy of 27K, and under that 27K, there will be four states. One is 151, 115, 511, and 333. All has the same energy. So degeneracy will be four under that energy level. Okay. So that you have to
Okay.
consider. Degeneracy means obviously total number of state present under the same energy. Eigenstate present. Okay, so that's clear. Now, what was our expression? If you remember, nx, ny, nz, it was k nx
N
squared
square plus N
whole
square plus
square plus
NZ
nz
square.
square. And what is our k? Where k was h square by
H
8
square by 8 square.
8 square. Correct. So now among these three, we are considering only two variables, nx and ny. Let's say we are taking nz equals to 1. We have fixed the nz, that is 1. So we are not considering the nz right now. So we are now just considering nx and ny. These two variable can vary. These two can take any value between 1 and infinity, and nz we have kept constant. Under this condition, so you can write like this. Just understand this thing. This is a very uh, beautiful argument. Okay, if you plot nx and ny, okay, we know that nx and ny can take only the integer value, right? So it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Here also 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So these two variables we have taken. Okay. Okay. So now let's just understand when it is 1 and 1, this point, if you consider this point, so what will be the energy of this point?
Z is also 1.
Yes, we have taken Z is 1. NZ1,
3K.
NZ1 we have taken. So what will be the energy? 3K, correct. So this point will signify a eigenstate which has the energy 3K. Okay. So this is this point 3K. So each point you can understand under this plot, if under this box, each and every point will signify an energy state. So let's say arbitrary, this point. This point will also signify energy state which has the energy 36 plus 16 plus 1. So it is 53K. Correct? So in this way you can do. Am I clear? So in this way you can do it. Okay. So these points are actually represent each and every energy state. Okay. So now just understand this. This is very tricky. So each and under this box, under this box, each and every point will signify a energy state. Okay. So if you are considering only two dimension, here we are considering two dimension. Actually, this two-dimensional figure is actually valid for our. You can understand this easily. This is for actually particle in a 2D box. Correct? Because in case of particle in 2D box, this will be the energy. The same thing. Uh, Under that case, it will look like this. Is it clear?
But Z is also here.
No, no, no. For 3D
It
box,
has
it's correct.
constant value.
Because I was arguing with 3D box. When in case of 3D box, if you keep constant one variable, then it will reduce to a 2D box, right?
Yes.
So that's why. But this is general. This is actually general expression for a 2D box, particle in 2D box. In that case, only two variables will be there, nx and ny. So in case of particle in 2D box, this will be the entire space. These states are
Then what
available.
is the energy?
Yes.
Then in case of particle in 2D box, what is the energy? 2K or 3K in one
Okay.
position?
Yes, yes. Obviously, then it will be 2k. This way, it will just you can take this value. It will be obviously 18k. There also energy will be different, but each point, our concern is that each point will have the will signify a particular eigenstate. That is important. Sure. In case of 2D box also, you can have the accidental degeneracy. Just you can see here, this 3 1 point, let's say I'm just saying, this 3 1 point has energy 10k, right? For 2D
10K.
box. This point also has the energy 10k. So these 2 points are
Yes,
the
1K.
actually degenerate state. Correct. This way, if you consider this will have energy 8k. So here energy is not same. For a particular point, energy is not same. But it's clear that each and every point is signifying a eigenstate. That is important. You can take any point. Let's say this point. This point obviously has 7 and 5. So 7, 49, 25. So it is 74k. This point will
4K.
signify the energy state of 74k. Like this. And this is not cost up to 10. You know, nx and ny can be 1 to infinity. In principle, there is no limit. In principle, there is no limit. So it can be, right? Okay.
Yes.
So now, if you consider a sphere, just you can see like this. Just let me draw it like this. So we are dealing with, just look at it very carefully. This is only one coordinate among four. Why we are dealing with only one coordinate? What does I mean? If you see the whole picture, then it will be only we are dealing with 2D box. Okay, I will then discuss 3D box. 3D box will be the same. If you see nx and ny, then you have to take the whole picture now. But why we are considering only this part? Can you say it? Why we are considering only the first coordinate, or not the second, third, or the fourth one?
Around the fourth one because nx and ny has to be positive.
Exactly. Nx and ny has to be
Exactly.
positive. Exactly. So this should be the positive. So if you consider the whole sphere, whole coordinates, four coordinates, then it will form a, like this. No, it is not a sphere. It is actually a circle. Okay. Under this circle, all states can be accessible. Here, this part is present. This is I have drawn. This part of that circle is present. Okay. So is this clear? So this is important. What does it mean? This can be important. Why I have considered a circle? This circle means that because let's say this circle will pass through a point, obviously. Let's say this is a point. So this point will also have a energy, correct? If you consider here also, this passes through a point. Let's say this point will also have energy. Okay, so if you see here, if you draw it is not up proper in scale. Okay, if you draw proper with a scale, you will see that the states present in the circle will have the same energy like this. Okay, so that is important here. That will come how it is happening, but we are considering this circle of the radius. Let's say this we are considering just the radius, that is n. Okay, what will be the value of n? N will be
Under root x square plus y square.
exactly n x square plus n y square, like this, or you can write it like this. This will be the value of n. Okay, so this is the number of states present in this. So you can consider any, just understand it, any circle. Okay, instead of this circle, let's say for this is n. Instead of this, if you choose another circle, let's say I am choosing this circle. This is smaller than previous one. So for this n will be different. Just understand what I want to mean. It may be confusing, but it's not difficult. It's easy. So when you say this is n, let's say n is 50. Just I'm saying n is 50 or n is here you can see. So let's say I'm considering n is 20k. So what is the point of 20k? 20 is, let's say for 20, is there any point for 20? 4 and 2, yes, 4 and 2,
4 2.
4 2. This is a 20k point. So take this point, and if you draw a circle, because my drawing may not be perfect, like this, it will form a circle when you consider all four dimension. Here also, if you see, let's say 4 2 point, any point 4 2, this is the 4 2 point. So around this 4 2 point, if you draw a circle like this, yes. So it's not proper, but if you consider this, so then, and what does it mean that this is 20k? So and the points which present inside this circle, that should have the energy less than 20k. This you agree or not? This is important. Took any point, took any point inside this circle, that will have the energy less than 20k. Is this correct or not? Do you understand this?
3 4.
3 4, 3 4 is not present here. Okay, 3 4, 3 4, it's outside the circle.
Okay, not possible.
Not possible. That I am saying. So when you are choosing a particular energy 20k or any energy 50k, 60k, then you draw a circle around that point, and the point present inside that circle, that point should have the energy less than that 50k or 20k any. So instead of this, you can choose any point. Let me draw another one. Let's say a point, I'm taking this point. What is the energy? Oh, it will be 36 plus 25, so 61k. So if you draw a circle around this, like this, so if this is the point, this is not circle eventually. So let me draw a proper circle, otherwise it will not be matched. No, this is also not a circle. Yes, this you can say as a circle. So now this circle goes through this point. So take this point. What is the energy of this point? This will be 17k. So inside this circle, if you choose any point, you can choose this point, any point, the energy of the point will be less than 17k. That I want to understand, convey. Is this clear?
Yes.
Okay. So this is purely due to the geometry. Nothing is there. Nothing will the with this 1D box, 2D box, 3D box, nothing is there. This is purely uh, coming from the geometry. Here also. So instead of when you consider this n or n1, let's say first you consider the n1, then obviously if the circle is n1 and this is circle of radius is n2. So when it is n1, then the energy states, this energy state present inside the circles, that will be obviously and will have the energy less than n1, and the energy points present here for the bigger circle, that will have the energy less than n2. That is very clear. So that I want to consider. Okay, so if this is clear, okay, so now if you consider now 3D, what will happen for 3 dimension? So it's clear here it is 2 dimensional. So in case of 3D we will have another axis. So in case of 3D, that means particle in a 3D box that we have considered earlier. For particle in a 3D box, we have to consider another axis. So it will be nx, ny, and nz. Correct? So here, instead of circle, you have to consider the sphere. Is it clear? Because now there will be 3 variables nx, ny, and nz. So instead of circle, you have to consider a sphere. And the radius of this sphere is
Under
a.
root x square plus y square plus z square.
Exactly. Same thing, just I am extended to the 3 dimension. That's why first I discuss the 2 dimension case, because that is very clear to visualize here. But in case of 3 dimension, it will be a sphere. Okay. So now what we have to calculate? We have to calculate here. You can say, if you consider here a particular, let's say, let me draw it again. I erased it. Okay, this is arc. So we have to calculate the number of state present inside this energy state, energy inside this energy. This will be the number of state present. We have what we have to prove ultimately. We have to prove that number of quantum state present, that is way more greater than number of particle. That we have to prove. So we have to now calculate the number of quantum state present under this arc, and then we know the number of particle, and now then we can calculate it. So that we have to do. Okay. Okay. So this is clear. So now we are taking any energy. This is n. So it's clear. Here you can see the points which are inside this sphere, that will have the energy less than or equals to epsilon n. Okay, I will do step by step. Is it clear?
Yes.
Here also the same thing. Here we can see, if this has the energy 20k, then the point inside this circle, the energy will be less than 20k. Here instead of 20k, I made it a general epsilon n, because this is n, this variable is n, so energy will be epsilon n. So the points present inside this sphere, that energy of that points will be epsilon, which should be less equals to epsilon n. So this is clear. Okay. So now let me now zoom it. Okay. So now, if you understand this, then it is nothing. It is clear. It will be easily understandable. So now we are defining phi epsilon. That means number of points present inside the energy, epsilon n. So that, okay. So this is the number of point in energy, sorry, energy less, not less, in energy great less. Just that means epsilon, energy epsilon. Is it clear?
Yes.
So we are taking the number of points. That means just we have discussed the points present inside this sphere will have the energy less than epsilon n, and pi epsilon is that the number of points which present inside that sphere. That is the pi epsilon. Okay. So what will be the number of points? That will be, just see, 1 by 8 of the volume of sphere. Just see, for circle, what will be the number of points? Just consider only one circle now. This is, let's say, n. So we have to calculate the number of point present inside this circle. That means having energy less than epsilon n. So what will be the number of point? Just you have to consider this first coordinate of that circle. Correct? Is it clear?
Yes.
So what will be the volume of the what will be the area of that first coordinate? This area. One
pi
by
pi 1/4
of pi square.
pi n square.
N square.
Pi n square.
Pi n square. Correct. This will be the number of points. So here is, this is a sphere. So if you extend it, in case of 3 dimension, this is 3 dimension. So 3 dimension you have a sphere. So and you have to take only one coordinate where the nx, ny, nz are positive. So you are taking only one dimension, one coordinate, and there are 8 special dimension in a 3 dimensional coordinate system, right? So you can see from here 8. So that's why you have to take 1/8 of the volume of the sphere. The same thing, nothing new. So it is actually 1/8 into 4 by 3 pi n cube. This is the volume of the sphere, 4 by 3 pi n cube, and 1 by 8. Okay, clear?
Yes.
Okay, now we have to put the n. What will be the n? So before that, it will be eventually, if you cancel it, so it will be 1 by 6 pi n cube. And you know that epsilon n was n nx square,
Under
ny square plus nz square into 8,
to the
sorry,
power.
a square by 8m square, right? And you have written that n square equals to nx square plus ny square plus nz square. So it is eventually n square h square by 8m square. So from here you can write n is equal to 8m square into epsilon n divided by h square. This is under root. So is it clear?
Yes.
Okay, so just put it. So phi e will be, I'm just putting, it will be 1 by 6, then pi n cube. So pi and n cube means 8 m a square epsilon n h square to the power 3 by 2. So just expand it. So what will be? So it will be pi by 6 a by h cube 8m epsilon n. So these are the number of uh, energy level, energy state present inside the energy epsilon n. Okay, this we had to calculate. So we had now calculate. So this is the, let me write it clearly, number of energy states present or available uh, with energy less equal to epsilon n. Clear? So this is our,
Here 8m epsilon and 3 by 2 to the power.
obviously, obviously. That's fine. That's fine. That's fine. 3/2. So this is clear. Now, so this what will be the exact number? So there we have now consider something. Let's say we are considering a particular any quantum mechanical particle. So what will be the mass for that particle? M is the mass of the particle, A is the length of the box, epsilon is the energy. So then we have to, if you put it, just I'm giving an example, nothing is there. So let's say M is equal to 10 to the power 22 gram. A, that is a box length 10 centimeter, let's say, and temperature is 300 Kelvin. So if this is the case, then phi E will be 10 to the power 30. If you put there, then it will be 10 to the power 30. Okay, just put it because you know H, epsilon N, A, M, everything is known. So if you put it, so then you can obtain this rough value. I'm saying the rough value. I'll discuss in detail this thing, but rough value you can obtain. This will goes up to huge number. So this is in general number of molecular quantum states. This quantum states available to a molecule at room temperature. 300 Kelvin is a room temperature. It's much more greater than the molecules present in the system, obviously. So you can see number of molecule. What can be the number of molecule? If you consider Avogadro number of molecule n, then 10 to the power 23. So in case of 10 to the power 23, the number of states available is 10 to the power 30. So you have 10 to the power 23 molecule and you have 10 to the power 30 states. So just look at it. You have 10 to the power 23 molecule, you have 10 to the power 30 states. So you have 10 people and you have 100 seats, 100 chairs, like this type of things. It means that for each and every molecule, there are 10 to the power 7 number of accessible states. So means for a single particle, it has a 1 crore option to be occupied or to occupy an energy state. Is this clear? So like that, you have 10 to the power 23 people and you have 10 to the power 30 chairs. So that means that for each and every people, he or she has option to sit in one chair from 10 to the power 7 chairs, means from 1 crore chairs. So this is the options they have. Okay. So that means for each particle,
Every particle has this option.
yes, you have divided 10 to the power 23 by 30. Just consider 10 people has 100 chairs. You have 10 people and you have 100 chairs. Then for each and every people, how many chairs are accessible? 10 now.
10 there.
How you do it? 100 by 10.
Yes.
Here also I did the same thing. 10 to the power 23 molecule. Accessible states are 10 to the power 30. So how many states are accessible for each and every molecule? 10 to the power 7.
Yes.
So it's huge. Correct. So from here you can
Yes.
say that. So here you can say that phi E is actually very greater than n number of particles. Okay, so just put it pi by 6. This value we have calculated already. A by h cube 8m epsilon n to the power 3 by 2 is very greater than n. If this is correct, then you can write it pi by 6 12 m kbt divided by h square. Okay, how I have written this? From this line to this, just I have introduced volume. Okay, so what was the volume? Is this clear or I have to explain it? This is clear, right? H squared to the power 3 by 2, so it's h cube. and a cube is the volume. So just I have opened that, and if instead of epsilon n I have just considered n as. So that's why what is the form of epsilon n? It was, if you remember, so it is nx square
And
plus ny square plus nz square into
x square by 8m square.
a square by 8m square, like this. Okay, 8 to the power 3 by 2. What is 8 to the power 3 by 2? 8, if you calculate 8 to the power 3 by 2, what will you have? 8 to the power 3 by 2.
2 to the power 9 by 2.
1 minute, let me check it. Yes, 22 something. Instead of 8 to the, we have 12 to the power. This is written. So 1 minute, let me check why 12 is written here. Can you understand? 12. It is a final form, but we obtained up to this. This form is directly written in this in the book. So that you have to understand. The volume thing you have to understand. What is the volume? Volume is obviously a cube. A cube should be the volume. So a cube is clear. A square is clear. M is clear. So okay. So we have put that 8.
That
Let me just
eight
put that. Okay. Just put that
okay.
3 by 2 kBT. That we have considered. Correct? These things we have considered. Epsilon is equal to 3 by
Yes.
2 kBT from equipartition. That you have put it. Okay. These things are generally not mentioned explicitly in books, but this is our final form. So n by v is important. N by v, what is n by v? What does it mean? I understand this is called a thermodynamic limit. First or second class I studied number of particle divided by the volume. So this is the thermodynamic limit. So you can see here, you can see that when n by v that I mentioned, just put it here, you will see if the mass is higher or the temperature is higher in that case, or the low density means this number n by v, this condition will be favorable under these three situations. So this condition, when this condition will be favorable, when the mass is large, temperature is high, or the density is less, then this condition will be favored. Correct?
Yes.
So under these three condition, we can say that under these three condition, we can say that directly the number of accessible state is way more greater than number of molecules present in the system. GI very greater than NI. So that we can say it from here. Okay, and
This density is number density.
number density, number density. This is also written as rho n. Okay, that I'm not.
What is the significance of it?
Number density means, what is the meaning of density? Mass density means the mass present per unit volume. Number density means the number of particle present per unit volume. Charge density means the charge present per unit volume. Just it,
Yes.
like, so this is the number of particle present per unit volume. That is the case. And you have in last class I proved that when GI is very greater than NI, that means the classical limit. Under this classical limit, what we obtain that FD and Bose-Einstein reduces to Fermi, Maxwell-Boltzmann. Correct?
Actual volume.
This we have already. So this is not a bad option. So eventually you can see this is very trivial. This condition is generally you can obtain. So just you have to take because in general, while proving this, we have not chosen anything. In general, we have obtained. this lesson we obtain in general, but this will be more favored when these three conditions will be satisfied. So this is not wrong. So this is not wrong to consider Maxwell-Boltzmann just by dividing in factorial. That is not wrong, because you can do it. So when you are choosing the uh, high temperature, at least the room temperature, and the number density is low, that means the low pressure, like this condition, you can easily use the Maxwell-Boltzmann.
Maxwell-Boltzmann.
Maxwell-Boltzmann. So that's why in class or in till now we did that for quantum mechanical particle, indistinguishable quantum mechanical particle. We just put this, right. This we have already did Q,
Yes.
but this is not actually correct, because for Fermi-Dirac or Bose-Einstein, for quantum mechanical particle we should do Fermi-Dirac or Bose-Einstein, but using Fermi-Dirac or Bose-Einstein you can't obtain any such formula. This is valid for the indistinguishable Maxwell-Boltzmann. Okay, so this is just just a reduced thing. This is reduced under the classical limit. Okay, so this is that thing I wanted to discuss. Okay, so nothing is left. I will show some problem. I will discuss some problem from Fermi-Dirac distribution, and then you said that you want to understand the reduced density matrix. I will discuss little bit, not very details, just the basic. Then we'll stop it. Okay. So let me start with the problems. Can you just give me a minute for it to open? Okay. So what was Fermi-Dirac distribution and Bose-Einstein distribution? In last class I did prove that. For Bose-Einstein, what was that? Do you remember? Three formulas.
1 by e to the power beta exponent minus 1.
Yes. So it was written like Ni star, that means most population distribution, Gi divided by e to the power alpha plus beta I plus eta, and eta was 0 for Maxwell-Boltzmann, eta was plus 1 for Fermi-Dirac, and eta was minus 1 for Bose-Einstein. Okay,
Okay.
so this was the distribution. Okay, so after that you can we obtain that alpha and we can alpha and beta, these forms are already known to us, so you can put that alpha and beta, then you will have that in general definition. Okay, so how we can now have the alpha and beta, that is a problem question, right? So let me consider any one of these things. Let me consider Fermi-Dirac. So in case of Fermi-Dirac, this Ni star will be, Gi will be there obviously. So Gi e to the power alpha plus, 1 minute. In last class I did not show this. Just let me check it. This equation, up to this equation I show. Okay, so ठीक है करते हैं. So from here you can evaluate the distribution like this. Just first let me write. For Bose-Einstein, it will be, this is the distribution function for Bose-Einstein. Maxwell-Boltzmann we did. Maxwell, in case of Maxwell-Boltzmann, Bose-Einstein, it is eventually 1 by 1 plus exponential, not 1 plus, sorry, 1 minus e to the power e minus, or e, only e for the energy, e by kBt minus. Okay, so this is our for Bose-Einstein. Okay, just let me write it. This this proof is difficult. I'm not doing. You can see, but mu is not given essentially. Epsilon is there. And for Fermi-Dirac, it will be. That's why it is written as n and it is written as f, e to the power epsilon minus mu by kBt plus 1. Okay, so this is the distribution function for Bose-Einstein and Fermi-Dirac. These things I think discussed in the class last week. Okay, do you have gone through this?
Yes, little bit.
Okay, because this derivation is quite lengthier. You can see from this expression you can do it. For Bose-Einstein it is minus 1 and for Fermi-Dirac it is plus 1. So eventually you will obtain this. Just like in canonical ensemble you did now, like the same thing you have to do and you will have the same. It's not ready from here because it's not very lengthy. Let me, but it's understandable for normal without you do Maxwell-Boltzmann. For Maxwell-Boltzmann it will be just 1 by e to the power epsilon by kBt, like this. This this is the distribution for Maxwell-Boltzmann probabilistic distribution. For both Einstein and Fermi-Dirac, you will have this. This is the distribution. Mu is the chemical potential. So now let me write down the question because this derivation is quite lengthy. That's why I'm not going to that. But the expression you have to know. So this is called Fermi function or Fermi distribution function. Any name you can say. So Fermi function, which is defined as Fe, which is Fe equals to 1 by e to the power e minus ef by kBt plus 1 gives the probability of occupation of any fermion, here mentioned as electron, per energy state. Then the probability of number of electron at absolute temperature when E is equals to EF is okay. So this is a distribution function. Distribution function essentially signifies the population distribution in the energy level. Okay. So from here you can see what is the question. This gives the probability of occupation of electron or any fermion or energy state. Correct? Then the probability of number of electron at absolute temperature when E is equal to EF. We know these are the fermions, and you know that for fermion the occupation may be either 0 or 1. Okay, so let me just write it. So this is our Fermi function, which is actually 1 by 1 plus exponential E minus EF by kBt. EF is called the Fermi energy. EF is called the Fermi energy. So just put when, let's say this, what does it mean that we have to understand? When Fe is equal to 1 for any energy state, Fe is equal to 1, that means that energy state is filled by one particle. This is probability, obviously, not 1 means 100%. That will be 100% filled. And if E is 0, that means that is empty, totally empty or vacant. Clear? So you can see when this will happen. Just put the value. So now it's very straightforward. Let's say when E is very greater than EF, E is very greater than EF. If you put it here, E is very greater than EF, then this will be very large and Fe will be 0. So that means Fe will be, in that case, will be 0. And when E is very less than EF, then Fe is 1. This is clear? I'm just discussing the fact, the characteristics of the Fermi function. These things you can directly conclude from the expression of the Fermi function. I'm not doing anything. Okay? Okay. So, and when E is equal to EF, then what will happen? Just put E is equal to EF.
0,
No, half,
1.
half,
Sorry, half.
half. So that is very important. When the energy is equals to EF, Fermi function, then the Fe will be half. Now, pictorially, if you want to understand that, let me understand, then it will be very clear. Let's say these are the energy states. I'm just put a box here. These are the energy states available to that fermion or electron. And let's say this is our EF arbitrarily. It means that what the Fermi function means, that you have to understand. So when just I'm doing from here this discussion, you can say the Fermi function is eventually bounded by this 0 or 1. It may be in minimum value is 0. When it is 0, when this factor E minus EF by kBt, this factor essentially when goes infinity, then it is 0. Correct? And when it goes 0, this factor, then it is 1. So eventually Fermi function always remains between 0 and 1. Okay. So now here they have said that we have to consider the absolute temperature, absolute 0 temperature. So temperature is very tends to 0. Just understand it. When temperature is goes tends to 0, just now if you put E is greater than EF, E is greater than EF, and temperature is 0, then this factor will be infinite. Correct? Is it clear?
The exponential term is 0.
No, E is greater than, I'm saying E is greater than EF, and t is tends to 0, then
Then it's infinite.
infinite, and Fe will be
Zero.
0. Correct. So that I want to mention here. So we can write it. So from the above discussion, so let's say Fe equals to 1. Mathematically, we can also show if Fe when Fe will be 1. So if you put it, Fe is 1 by 1 plus exponential E minus EF divided by KBT equals to 1. So if you do it, so you will obtain that exponential, that things we have already discussed. This factor should be 0. Mathematically also you can show if it is 0, then it will be. So when it will be 0, that I have already said that it will be 0 when t tends to 0 and E is less than EF. Just look at it. E is less than EF, so that is a negative, and t tends to 0,
Negative infinity.
so it will be infinity, correct?
It will be for negative infinity.
Yeah, that is negative infinity, nothing. Infinity is infinity. So 1 by infinity is obviously 0, nothing is there. That should be okay. So this is the case. So let me prove it in reverse way. So we are saying when t tends to 0 and E is less than EF, then it will be this part. E is less than EF, so it is negative, exponential negative. So no, no. So one, what I'm saying, E is less than EF. Under this condition, exponential E minus EF by KBT. What will be the this e to the power? This
Zero.
is minus infinity, correct?
Yes.
So it is e to the power minus infinity. Okay.
Yes.
So if it is e to the power minus infinity, so it is e to the power infinity. Okay. That means it is 0.
Yes.
So this exponential part, this part is 0. So Fermi function will be Fe will be 1 by 1
One.
plus this exponential part is 0. So it is 1. Is this clear? Don't be confused. Just look at it.
Yes.
Okay. Now take the other limit. Same thing when t tends to 0 and E is greater than EF. Just the same thing. If this is the case, then exponential E minus EF by KBT. See here, this is now this is e to the power infinity, not the minus infinity. Correct?
Yes.
So this is e to the power infinity means infinity. So put it. So okay.
Okay.
So it is very clear that so what will be the plot? If you draw the plot, it will be very easy to understand. So what we have obtained, this is very famous plot for Fermi function. Here the Fe and here the E. And let's say this is the Fermi function EF, and it is when T is tends to 0. Okay, so when E is equals to EF, it is half. When E is less than EF, we obtained it is as 1, and here it is 0.
0.
So it will behave like a step function. Okay, so this is 1, this is 0, and this is a step function. That's why when E is equals to EF, it will take a intermediate value, that is half. It will just jump. What does it mean? It means that in physically, if you look at that plot, yes, it means that when the energy is less than EF, this is totally filled. That's why you see the F is the occupation probability, correct? That is 1. That means it is totally filled. And
Complete probably.
when E is the greater than EF, that is totally empty. So that's why we consider that the energy state which are less than Fermi level, that energy levels are completely occupied, totally occupied. And the energy
In
levels
any temperature.
in zero temperature, obviously. If it is not zero temperature, then what will happen, I will discuss. But at zero temperature, it is clear that when this is less than Fermi function EF, then it is completely occupied, and when the energy levels you are considering, that is the energy greater than EF, that are totally vacant. So this is the importance of Fermi function, Fermi energy, sorry. And this Fermi energy is essentially equals to the chemical potential mu. This is called the chemical potential. This is the way you can define the chemical potential. Okay, so this is the mu. This is the step function. Now you see, if it is not t tends to 0, you are not considering now t tends to 0, then what will happen? Then this will look like distorted. As much you increase the temperature, this deviation will increase, but it will go when equal to F, that will always be half.
In the first case, where it is half.
Just 1 second, let me draw it, then I will yes, ask what,
In
just
the
put,
first step.
yes, when E equals to F, this case.
No, no, in the graph.
Okay, in the graph, this is a jump. So when you are considering a step function, this kind of function is called step function, right? Uh, this type of functions are called step function.
Yes.
In case of step function, when there is a jump, then you have to take the average value, because there is a jump, that is a discontinuity. So in case of discontinuity, you can't get a particular number. So in that case, you have to take the average value of that jump. So it is jump from 1 to 0. So that's why you have to take the average value. What is the half? Okay.
Okay.
So actually, if you zoom it, then you can understand it like this. If you zoom, actually, this is like this. It will get narrower now when it goes t tends to infinity. You can see this is the high temperature T1, T2, T3. As much you decrease the temperature, it goes to 0. Then the plot will be more narrower. The temperature is less, then it will be like this. Again, you decrease the temperature, it will go. So at particular
Okay.
0, it will just behave like a step function. So that's why you have to take the average. Okay.
Okay.
So that means if the temperature is not 0, why drawing? So in that case, you can see, as the temperature is not 0, in that case, when E is less than EF, then you can see this part has the occupancy less than 1. When it was 0, when T was 0, when E is less than EF, when E is less than EF, each and every states are occupied. here. But when the temperature is less, you can see some states, these states are occupation less than 1. These states are some states will be there which are closer to the EF, that will have occupation less than 1. What does it mean physically? That means that has a temperature. So some particle will be excited to the energy states which has the energy greater than the EF. Okay. So that's why you can see here some states will be there which has the energy greater than EF, has the occupation greater than 0. Is it clear why it is happening?
Yes.
Because it's not zero temperature, it has some energy. So these states which has the very less energy compared to EF, that means these energy levels, it has complete occupation 1. And this energy state which has the very greater energy compared to EF, this is totally vacant. But in between levels, some excitation occurs from this to this. So that's why these states are not completely 1 and these states are not completely 0. That is less than 1 and this is
When it
greater
is
than
not absolute zero.
when it's not absolute 0. At absolute 0, it will be completely a step function. At absolute 0, when the energy are less than EF, it will be completely filled, and if the energy is greater than EF, it is completely vacant. But when the temperature is not absolute 0, it will be excited. Some particle will be excited from these states to that state, below Fermi function to the above Fermi function states. That will happen. Okay. So finally, what we can write the Fermi function Fe as this is the general form of Fermi function that is widely used. Or you can directly write it. Okay. So this is the form of Fermi function. So one more question we can do from Fermi function. I think it's clear. So next question from Fermi distribution. This question we have done. Yes. In this question, what was the main question? Main question was that when E is equal to EF, then for E is equal to EF, it is always half. That is independent of temperature. You can see when E is equal to EF, that is always half. That does not depends on whether temperature is absolute 0 or not. Okay.
Okay. In
Okay.
infinite temperature?
What does it mean by infinite temperature? Any temperature can be infinite. These things I have already said. Na? That will depend up on this value, E minus EF or E minus mu. That will dictate what will be considered as infinite temperature. Just understand
Okay.
when it is infinite temperature, let's put T is equal to infinite. That means this exponential part will be vanishes. This part will be 0 and e to the power 0 is 1. Correct?
Yes.
So that means each and every state will be independent of E, because temperature will make this function as half. So if that is the case, so for each and every state occupation will be half. Okay, so that is not feasible case. That means you have infinite temperature in infinite. What is the definition of infinite temperature? That we have already understand. At infinite
When
temperature, the
all the states equally
will be
populated.
equally populated. That is happening here also. All the state will be equally populated. That's the case.
But these two levels are only equally populated. This under EF and above EF. All are equally populated.
All are equally populated. There are not only two levels. Under EF means all levels present in this domain. There not to be
Okay.
only one level. There may be infinite number of levels.
Okay.
using Fermi function evaluate the temperature. Okay, now your question, something like related to temperature, at which there is 1% probability that a state with an energy on 5 electron volt above the Fermi energy will be occupied by an electron. Do you want to try it? Just same thing already we have discussed.
But where I will apply this 1%?
Just understand, if it is a absolute zero, what they have asked? They have asked that 1% probability that a state with an energy uh, 0.5 electron volt above the Fermi energy. So you have to consider a energy state, let's say this energy state E, which is above the Fermi energy F. You know that if it is absolute zero, then it as this state is above Fermi energy, it should be zero occupation number.
Yes,
But you have to identify the temperature for which it will not be zero. It will have the 1% probability. 1% probability means F will be
1 by
1%, 1 by 100, so 0.01. That you have to calculate.
okay, then I'm doing.
Okay, just try it, then I will do. Okay, so let me also do it. So we have to just find out Fe, that Fe is equal to Ef plus 0.5, correct? For which it is
Yes,
0.1, 0. So this is 1 by, just I'm writing 1 plus exponential E minus Ef divided by kBt, that is 0.01. So it will be 1 plus exponential E minus Ef is now 0.5 by kBt. This should be 100.
yes,
Clear? So this is the case. Then it will be do exponential 1 by 2 kBt. It will be 99 exactly.
log 99.
So a, yes, ln 99. So kBt will be
Approximately 2 ln99.
ln 99 will be there. So it will be 2 into ln 99.
Yes.
So temperature that will be kb to 2 into ln 99. That you have to calculate. So what will be ln 99?
1.9 into 2.303.
So it is give a calculator is giving ln 99.
No, I have no calculator.
So what is the value of ln 99?
Approximately it should be 2.303 into log 99. That means approximately 2.303 into 2 nearly.
Exactly, exactly. So around 5. So its actual value is 4.595 is. So it will be 4.5 into 2 into kb. kb is, so it is 1 by 12.68 10 to the power minus 23.
26.
No, one thing is there, sorry. Oh, oh, this is electron volt. This you can't ignore.
Oh, by
Okay.
charge of electron it's
So that is
24.
electron volt, 1 electron volt. And 1 electron volt is
1.6 in 10 to the power minus 19 joules.
19 joule. That you have to consider. So now you can say it will be, just calculate it, it will be 0.62 into 10 to the power 4. So it is, just check it. Is it clear?
Yes,
So you can see, just to shift 1% of population uh, which is above Fermi function, the energy, the temperature needed, that is around 1200 Kelvin. So it is way beyond the room temperature, correct? So this is a huge temperature, but that is possible. Here also that depends on the energy gap between the Fermi function and that energy level you are expecting to have the occupancy. That here it is 0.5 electron volt. That is also matters. Okay, so last question
yes.
we want to do from this Fermi function, then we will discuss the density matrix little bit. So last question from this Fermi function. This is very easy. You should do it. The Fermi function, the Fermi, let me write. 1 by 5 plus this definition they are giving, just arbitrary definition. You have just given this is the definition of Fermi function. You don't know why. If it is, just consider gives the probability of occupation of electron per energy state. That's same definition, just instead of 5 1 it is 5 there. Then the probability of number of electrons at absolute temperature, absolute zero temperature, I mean, when E is equal to EF. The same question we have already done, but here the Fermi function is different. We have to find the F when E is equal to EF. So what will be the answer?
1/6.
1/6, because this will be exponential 0. It's 1/6. It's just straightforward. Okay. So this question related to Fermi function has already done. Now little bit we will discuss the density of density matrix, right? For operator. Okay. So I will not go very details because this is very not very basic topic. Just I am defining due to uh, density operator is a very powerful approach basically. Correct? Because uh, you have heard about DFT, density functional theory, but density functional theory has very limitation. But in case of density matrix approach, it is very generalized theory. You can apply it for any system. Just I'm defining what is the density operator and what is the definition. This is purely a mathematical background. Let's say the basis state is important. So in quantum mechanics, you know, just if this is a eigenstate, right? Psi. You have a quantum system, a system. So for that system, psi is the eigenstate. If psi is the eigenstate, then uh, what does it mean? That you have to first understand. Psi. Okay. What does it mean? Or do you know inner product?
Inner product.
Yes.
I think I
Or
don't.
okay, you don't know. Okay. Or vectors. Yes,
Vector space.
vector space, you know, Hilbert space, basis.
Yes.
These
No, no,
things you
no.
know, right?
Basis, yes.
Basis.
Dimension basis, I know.
Okay. So let's say, okay, forget about these things. Okay, these are mathematical definition. I'm not going into that. This psi is a in mathematics, the vector is not that vector you study in physics. That is not the vector. You know, the vector is called which actually follows the set that called the basis set, the rules that call the vector space, forms
Combination
of
of
vector
vectors.
space. Yes, that associative rules, some the spanning, these criteria should be followed. But I am not going to details. This is not important. This is not important because we are considering this psi, these are actually vector belongs to vector. These wave functions, these eigen states are essentially belongs to Hilbert space. This I just consider. What is Hilbert space? That is not important. This is a different things. But let's say that quantum mechanical wave function you have studied the same thing. This is the psi. So when you have studied this psi m psi n, what does it mean? Just consider any quantum state psi n. You can write that quantum state, any quantum state psi n, in terms of linear combination.
Yes,
This you know, right?
yes,
So when you are applying this, that essentially means that this Okay. So,
Yes.
and you know that orthonormality, when m is equal to n, when this I will take every value, when will equals to m, then only it will survive, otherwise it will be 0, the Kronecker delta.
Yes.
So essentially it will be
Yes.
Cm, correct?
When m equals to n.
No, psi n is the total wave function. That is a linear combination of all wave function. Psi 1, psi 2, psi 3. These are the all wave function, right? So
Yes.
when I project psi m, that the bra part psi m, if you operate this, then you will have this. So you see that essentially, if summation you can take out like this, and I will vary. So you see here, you know that psi m psi n is essentially the Kronecker delta. So it
Yes.
will survive when I will take the value m, otherwise it will 0.
Yes.
So summation will goes away. So and you will have the only Cm.
Cm. Yes.
So what does it mean? It means that you are what this is called inner product. Okay, inner product of psi m and psi n. This means that you are having this is some probability. When you take the mod, it will give us the probability. That will say the probability of having psi m in the psi n. In psi n, it has all the wave function, linear combination of all wave function. So when you are taking the inner product, so it will say the probability of finding that wave function in psi n. When you take the mod squared, essentially it will be Cm squared. This is the probability, and this is the transition probability used in the spectroscopy also. The same thing. So that's why inner product is important. So if you take any two arbitrary inner products, psi m and psi n, that means that having probability of psi m in the psi n. It means that what is the probability of finding psi m in psi n. You have the two energy state, let's say n and m. So if you calculate this, and you are having this 0, that means there is no transition. And if it is some value, let's say 0.5, and you have take the mod square, that value signifies the transition probability. That means transition. What does transition means? Transition means the having probability of something psi m in the psi n. That is signified by this inner product. That these things you will be understand when you study the spectroscopy or quantum mechanics in details. But the same thing. So when instead of this psi, if you apply this is not a inner product. This will give you a number, correct?
Yes.
This is a vector, psi is a vector, belongs to Hilbert space. When you are
Yes.
taking inner product of two vectors, this is inner product of two vectors, this will gives you a scalar, a number. Here you have obtained Cm, this is a number, that means a scalar quantity. But this is not a scalar quantity. This is a operator. These things you have to understand. Nothing is there. Just these things. You have just reversed. This is a operator. Operator, what does operator means? Operator means, let's say A is a operator. When you operate A on a psi, you will have a eigenvalue, right?
Yes.
If this is the eigenfunction, same thing. Let's say if you operate this psi, these things on any other, let's say here we have done it. So let's say psi n. Then what we will have? Delta mn. So
Yes.
and you know that Kronecker delta, it will be 1
Cm.
where, so you will have the psi n. Clear?
Phi n.
Just see, when m is equal to n, then only it will survive.
Yes. So it
So
should have m.
no, m is there. So if m is equal to n, then it is just from here you can write it. When m not is equal to n, then it is 0,
Yes.
and m is equal to n. So what do you want to write? Psi m, right? Correct. Connector delta is 1, so it will be psi m. Is it confusing? Okay, let me write it. This is 0, correct? This is clear. This is clear.
Yes.
Okay, so you can write it,
Yes.
and m is equal to n. So just instead of n, I
So
can
it's
write
n.
n. So see, ultimately what you have, just look at it in a different way. So this is operator. You are having eigenvalue of 1. Okay,
Yes.
so that's why this is not inner product. This is an operator. So this operator is called the density operator. If there is only one state, then it is psi, nothing is there. If there is more than one state, then you have to take the summation, and probability will be there. I don't know how many states are there, but this is the general form. Okay. Oh,
Both psi will have psi I.
psi I. Huh. Same psi. Here you
If
see,
one is psi j,
no, that will be not act as operator. That is not correct. In when this is operator, the both index should be same. This should be same. Then it will be the
okay.
operator. And why pi is given? Because obviously probability will come. If there is not only single state, here also probability appears na. When you are take linear combination, the probability will appear. I'm not going details the derivation, but this is the sign.
And
Okay.
where is the matrix?
Now you can form the matrix. This is density operator. If there is only two states, then it will be a matrix. It will be like this.
Both should not have same
Should not
psi
have
1, psi 0. One is psi 1 and one is psi
Yes,
0.
yes,
So,
psi 1. This will be
no,
the
in the
matrix.
third position.
Third position 1 0.
But yes,
Yes, row 1 0
so
is
it is
there.
not operator.
No. That okay. What you have okay. These are called the off diagonal operator. Okay. These are
Okay.
these are off diagonal terms. When it is 0 1 or 1 0, that is the off diagonal term. It will
And
have a
this
different
diagonal?
it will have a different meaning. So in case of diagonal term, it will have it is density of it is also called the density operator, but it has a different meaning. It is basically signify the coherence. Okay, so this is quite tricky. In general, you remind this will be the psi I.
If I
Okay,
take n by n matrix,
then it will be in state. How many states are there? That is important. I means these are the number of state, means the number of bases. So okay, so to be honest, I can be different. But here, if you look here, I how you can put the I different? That is not possible, na? That is not possible. So that's why I said So here, if you have n bases, n dimensional bases, then it will be a n by n matrix. So by this way, you can
Okay.
define this the row. But it is very vague way I just discussed you. That's why these confusions are arising. But later, when you study the density matrix, it will be very clear, and there is no ambiguity in density matrix. So this
In which
trace,
part is it?
yes,
Is it in quantum mechanics?
no, it will be in statistical mechanics, quantum statistical mechanics.
In
Okay,
BSc?
I will upload a short note. Some notes I have to upload. That quantum mechanics you have said that I will upload, and this I will prepare a summary of 2 page that I will upload. Okay, so that
Okay.
you can go through and you can ask me if there is any doubt in WhatsApp. I will say
Okay.
because
Thank you.
this is quite tricky. I have to write something, then you will
Yes.
understand. Okay. So it's not better to discuss these density matrix further. Okay. So rest of the part I will discuss. But the basic you have understand. This is the basic of density matrix. When there is only one state, nothing, no confusion is there. But when more than one state, some confusion will arise. That I will share the note and you will understand that. Okay.
Okay.
Okay. So do you have any other doubt? So you can ask me. You said that after.
So many doubts. So I think I will do it in WhatsApp. And now please clear one doubt. Uh,
Okay.
I was studying equilibrium. So how to relate the equilibrium constant with the partition function?
Yes.
In
That
Macquarie book I was reading,
okay.
I am unable to understand anything.
From Mercury, you will not understand anything. But this is already discussed in class. Equilibrium constant with the partition function.
Yes, but I think it's a little
That
bit tough.
that you want to say that the things discussed in class that was not understandable to you. You did
No,
not
but
understand
that
that,
means
right?
yes.
Okay. So what can we do? Okay.
Do you
So
have any?
don't go through the Mercury book first. Okay. Don't go.
I want that because the normal equilibrium is very easy. I can do that.
Okay.
But
So
I want some advanced.
one thing you can do, whatever you have studied, that materials you can share me on WhatsApp. I will go through it and then you can ask me the question. Then particularly I can understand where the doubt is.
Okay.
Okay. So because this is the last class,
Okay.
so I will not be available for this class, but you have my WhatsApp number, so you can ask me. Okay, there. If needed, I
Okay.
will share you the notes or voice messages, or you can call me. That there is no problem.
Okay. Thank you.
Okay, so you can share me. I will because for that I have to just check the PDF or the notes or the books from where you are having the doubt. So then I will clear it. Okay.
Okay.
Okay. So let me stop here today. If anybody have other doubt, any other doubt, so then you can ask. Okay. So nobody is given. Okay. So now you are giving the exam right for this course.
Yes.
Okay. When is the exam?
3rd October, 3rd November.
Okay, so there is a time. So there was one request I received for having the summary or extra class, but I forget to fill up that form. Otherwise, I will have one more 1 hour class. But okay, it's still
Oh,
you can send me the doubts in WhatsApp. Okay.
okay.
Okay, so let me now stop here. Okay, it was very good for this course, 12 weeks course. Okay. Again, hopefully. Oh, you can send me the doubts. We will be touching WhatsApp.
Okay. Thank you.
Oh, okay. So Now I can.